Welcome to the Explainer. Step into the dojo because today we are mastering Cambridge Computer Science exam strategy. Our core philosophy for this session, flow like water. You need to adapt your style to absolutely any question that comes your way. Let's dive right into the challenge. Picture an actual past paper question focused on hexadecimal representation, the kind you'd see across Cambridge syllabuses like 0417, 0478, 2210, or 9618. I want you to imagine two students tackling this exact paper. First, we have Alex. Now, Alex is a workhorse, but Alex has a critical flaw, overloading answers with raw, unfiltered computer science facts and providing absolutely zero analysis. The examiner asks a question, and Alex just dumps the textbook onto the page. On the other side, we have Sam. Sam actually understands the underlying concepts beautifully, but is constantly rushing against the clock, completely missing the specific requirements of the command words. Look at their answers. Alex gets hit with red pen marks for being off topic, and Sam gets penalized for lacking detail. They both miss out on top marks for the exact same underlying reason. They are treating hexadecimal representation as an isolated vocabulary word. Our mission today is to transform your approach. We're moving way beyond rote memorization. We're going to build adaptable, exam-ready reasoning so you can secure every single mark available no matter how the examiner twists the scenario. So, let's break that novice trap of rote memorization right now. Before we touch the terminology, we have to understand the practical purpose of the concept. Ask yourself, what digital problem does hexadecimal actually solve? Alex's immediate trap is just vomiting facts. Alex writes, it's base 16. It uses digits 0 to 9 and letters A to F. Okay, great, that is factually correct, but it completely fails to answer the question of what problem it solves. Sam's trap is rushing right past the command word solve and just giving a vague summary. Listen, hexadecimal isn't just some mathematical curiosity invented to torture students. It is a highly specific tool engineered to solve a very real digital problem. And here's the secret. Computers literally do not care about hexadecimal. A CPU only processes electrical states, represented as binary ones and zeros. Hexadecimal is entirely for us. It solves the massive problem of human error when technicians are forced to read, write, and debug incredibly long strings of binary code. It compresses 4 binary bits, a nibble, into a single hex character. That makes it infinitely easier for human programmers to configure networks, manage memory dumps, and spot errors. If you don't truly understand that foundational why, any tricky scenario-based exam question is going to completely knock you off balance. You have to know why the tool exists before you can explain how it works. Here is our roadmap for this explainer. Think of this as your training syllabus for the day. First, we'll push beyond rote memorization. Second, we'll dive into the 3-layer method for deep understanding. Third, we'll break down exactly how to structure your exam answer. Fourth, adapting to real-world contexts. Fifth, dodging those common examiner traps. And finally, the ultimate self-check to prove you're ready. Section 1. Beyond rote memorization. To actually move beyond just reciting facts, we have to treat hexadecimal as part of a connected, living web of computer science ideas. We do this by utilizing the PEAL framework. That stands for point, evidence, explanation, and link. Look at the critical contrast on your screen between a description and an explanation. A description merely tells what the device, process, or method is. An explanation goes deeper. It tells how it works and exactly why it matters in context. Cambridge examiners absolutely expect both. If you only describe hexadecimal as a base 16 system, your answer is safe, sure, but it's incredibly shallow and caps your grade. Conversely, if you jump straight into explaining why it prevents human transcription errors without first defining the concept, your response lacks foundation and sounds confused. The real magic happens when you fluidly cross the boundary from description into explanation. You make your point, provide evidence, explain the mechanism, and link it back to the question. You have to explicitly train your brain to recognize when an exam command word like explain or evaluate is demanding this deeper level of analysis. And hey, before we continue diving into these command words, subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. It's the best way to ensure you're getting all the strategies you need. Now, let's get back to recognizing those command word triggers. Section 2. The 3-layer method. If you want to build a truly robust, flexible, water-like understanding of any complex computer science topic, you need a systematic training regimen. We call this the 3-layer method. Layer 1 is your simple explanation using everyday language. Imagine you have to explain hexadecimal to someone who has never used a computer. You'd say, it's a clever shorthand way to make super long strings of computer numbers shorter and much easier for humans to read. It's basic, but it proves you grasp the core utility. Layer 2 is the technical explanation, where we introduce the correct subject vocabulary. Here you'd say, hexadecimal is a base 16 number system used as a human-friendly abstraction of binary data, where exactly 4 bits are represented by one hex digit. Now we're talking like computer scientists. But layer 3 is the ultimate goal, the exam explanation shaped specifically for intense time pressure. This is where you deploy that PEL framework while the clock is ticking down. Now, so many students, just like Alex, mistakenly think they've mastered a topic when they comfortably reach layer 2. But when they sit in the exam hall and the pressure hits, they completely freeze because they haven't practiced layer 3. You must practice retrieving and structuring this information under simulated pressure before you ever step foot in that exam hall. Now, I need to issue a major warning here. Avoidable, heartbreaking losses of marks happen constantly when candidates recognize a familiar word but proceed to answer entirely the wrong question. Surface features in an exam prompt are dangerous. Seeing a buzzword like MAC address can totally hijack your brain and distract you from the actual process being tested. For instance, a classic Cambridge question might ask, explain why hexadecimal is used to represent MAC addresses. If you go off and write a beautifully detailed, grammatically perfect paragraph about how MAC addresses identify hardware devices on a local area network, you know what you score? 0. Absolutely 0 marks. Why? Because the command wasn't describe a MAC address. The question explicitly asked why hexadecimal is used. You fell for the shiny keyword and missed the deeper mechanism. The examiner is testing your understanding of data representation efficiency, not your knowledge of network topology. You must lock your focus onto the core demand of the question, not just the first technical term that catches your eye. Section 3. Structuring your exam answer. Stop scrolling! Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's talk structure. To avoid answering the wrong question like we just discussed, you need strict discipline. We rely on a precise 4-step sequence for constructing logical, undeniably clear answers, rather than just randomly shotgunning memorized facts onto the page. Step 1. Identify the exact demand of the question. Highlight the command word. Is it a state, a describe, an explain, or an evaluate? Each word demands a different depth. Step 2. Classify the correct concept. Are we actually dealing with data representation here, or is this a sneaky security question? Step 3. Explain the sequence step by step. Never jump from the beginning of a process straight to the end result. If the question asks how to convert binary to hex, you must detail the exact process of splitting that 8-bit byte into 2 4-bit nibbles first. Don't skip steps assuming the examiner knows what you mean. Step 4. Connect back to the context and check for any required judgments. If the exam scenario is about a smart home security system, your answer absolutely must mention the smart home. It is not just about what facts you know, it is entirely about how effectively you can deploy what you know into their specific scenario. A massive part of correctly classifying the concept in Step 2 is mastering what we call contrast boundaries. These are the critical definitional differences between similar-sounding concepts that dictate the entire direction of your answer. Think about the boundaries between memory versus storage, or a compiler versus an interpreter. Computer science reasoning relies heavily on you knowing exactly where these boundaries lie. In the context of hexadecimal, the most vital contrast boundary you must know is the one between hexadecimal and binary. Binary is the physical reality of the computer. It's the actual electrical states being processed by the CPU hardware. Hexadecimal is purely a conceptual abstraction designed for the human interface. If you ever write in an exam, the computer processes hexadecimal instructions, you have violently crossed a contrast boundary in the wrong direction, and you will lose the mark instantly. The examiner is actively hunting to see if you actually know where one digital concept ends and another begins. Section 4. Adapting to real-world contexts. Let's get interactive. Generic, context-free textbook responses rarely gain full marks in Cambridge exams. Examiners desperately want to see that you can transfer theoretical knowledge into specific, messy, real-world scenarios. Think about where hexadecimal actually appears. Mobile phones, HTML on websites, databases, automated systems, communication services, school management tools, banking systems, robotics, secure online activity. Right now on your screen, we're putting up a complex data table showing a system memory dump. You've got 60 seconds on the visual timer. Your challenge? Scan this data and extract the core trend. Look closely at the columns. What do you see? While the clock ticks, remember this. In websites, hex is used for HTML color codes defining millions of pixel colors. In communication services, it's formatting MAC addresses. In robotics, it's those low-level memory dumps we're looking at right now, used for debugging critical error codes. Hexadecimal is the universal translator between complex machine-level binary and human-level system management. Okay, time's up on the scan. Did you spot that the hexadecimal values in the error column were mapping directly to specific hardware faults? Your exam answers must stay locked inside the specific context provided. If the prompt is about a school management database crashing, your hex answer must explicitly explain how the database admin uses hex to read the memory dump of that crash, not just vaguely waffle on about how hex can be used for colors on a web page. Context is everything. Take a second to really absorb this quote on the screen. Real-world transfer matters because it converts memory into usefulness. Repeatedly forcing yourself to connect a dry syllabus topic to familiar everyday technology is what anchors it in your brain. It reminds you why the concept exists at all. Let's do another quick challenge. Find the flaw. I'm going to read a sample paragraph, and I want you to identify exactly which sentence is bleeding marks. Here we go. Hexadecimal is a base 16 system. It uses numbers 0 to 9 and letters A to F. It is better than binary because computers process it faster. Programmers use it to represent MAC addresses. Did you catch it? The fatal flaw is the claim that computers process it faster. As we established with our contrast boundaries, computers absolutely do not process hex faster. They literally can't process it at all until it is converted back into binary. Breaking that boundary shows the examiner a fundamental structural misunderstanding of the core mechanism, and it will cost you your justification marks, no matter how good the rest of the paragraph is. Section 5, Avoiding Common Exam Mistakes.
When we look through the strict lens of a Cambridge examiner, we can see exactly where smart students unnecessarily leak marks. You have worked way too hard memorizing the syllabus to lose points on sloppy logic. Let's look at the consequences in this table. Vague wording? It makes you sound confused and unsure. Missing process steps? It completely breaks the logical flow of a describe or explain question. Stating an advantage without providing the underlying reason, that instantly loses you justification marks. It is always better to logically explain the mechanism first before you state the consequence. Time for our final interactive workshop, speed writing. You have a 30-second timer on screen. I want you to mentally structure one perfect peel paragraph explaining an advantage of hex. Go.
Section 6, The Ultimate Self-Check. Before you ever declare that you have finished reviewing a topic, you must put yourself through the ultimate self-check. You need to ask yourself 4 vital questions. Number 1, what is it? Number 2, exactly how does it work? Number 3, where is it used in the real world? And number 4, why is it better or worse than a specific alternative in that exact situation? If you can confidently answer these 4 prompts out loud without checking your notes, you have successfully converted a flat vocabulary word into a dynamic, high-scoring exam strategy. This ties directly into the 3 rules of our final computer science answering system that guarantee top marks. Rule 1, command word decoding. Know exactly what depth the examiner wants. Rule 2, peel framework application. Structure your logic flawlessly. Rule 3, time management matrix. Allocate your effort based purely on the marks available. Now, listen closely. Students who implement these computer science strategies see an average improvement of 2 whole grade boundaries, but that only happens if they practice consistently with our weekly videos. So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by without having the best strategies in your corner. Drop a comment below right now with your target grade for computer science and the biggest challenge you're currently facing. Our team reads and responds to every single comment. Like and share this video with a study partner who needs it. Ace the Exams, your Cambridge success starts here. I want to leave you with one final provocative thought to chew on before your next study session. Look at the screen. If a complex exam scenario changes the context entirely, throwing you a situation you've never seen in a textbook, can you confidently paraphrase the core mechanism accurately without relying on your memorized wording? If you've been following these strategies and internalizing the peel method, the answer should be a resounding, undeniable yes. You are no longer relying on fragile rote memorization. You have built adaptable, bulletproof reasoning. Flow like water. Keep analyzing, keep adapting, keep practicing, and I will see you in the next explainer.